suppose the beginning of the universe was like the south pole of the Earth, with degrees of latitude playing the role of time. The universe would start as a point at the south pole. As one moves north, the circles of constant latitude, representing the size of the universe, would expand. To ask what happened before the beginning of the universe would become a meaningless question, because there is nothing south of the South Pole. Time, as measured in degrees of latitude, would have a beginning at the South Pole, but the South Pole is much like any other point, at least so I have been told. I have been to Antarctica, but not to the South Pole. The same laws of nature hold at the South Pole as in other places. This would remove the age-old objection to the universe having a beginning, that it would be a place where the normal laws broke down. The beginning of the universe would be governed by the laws of science. The picture Jim Hartle and I developed of the spontaneous quantum creation of the universe would be a bit like the formation of bubbles of steam in boiling water. The idea is that the most probable histories of the universe would be like the surfaces of the bubbles. Many small bubbles would appear and then disappear again. These would correspond to many universes that would expand, but would collapse again while still of microscopic size. They are possible alternative universes, but they are not of much interest, since they do not last long enough to develop galaxies and stars, let alone intelligent life. A few of the little bubbles, however, would grow to a certain size at which they are safe from recollapse. They will continue to expand at an ever-increasing rate, and will form the bubbles we see. They will correspond to universes that would start off expanding at an ever-increasing rate. This is called inflation, like the way prices go up every year. The world record for inflation was in Germany after the First World War. Prices rose by a factor of 10 million in a period of 18 months. But that was nothing compared to inflation in the early universe. The universe expanded by a factor of million trillion trillion in a tiny fraction of a second. Unlike inflation in prices, inflation in the early universe was a very good thing. It produced a very large and uniform universe, just as we observe. However, it would not be completely uniform. In the sum over histories that are very slightly irregular, will have almost as high probabilities as a completely uniform and regular history. The theory therefore predicts that the early universe is likely to be slightly non-uniform. These irregularities would produce small variations in the intensity of the microwave background from different directions. The microwave background has been observed by the MAP satellite, and was found to have exactly the kind of variations predicted. so we know we are on the right lines. The irregularities in the early universe will mean that some regions will have slightly higher density than others. The gravitational attraction of the extra density will slow the expansion of the region and can eventually cause a region to collapse to form galaxies and stars. So look well at the map of the microwave sky. It is a blueprint for all the structure in the universe. We are the product of quantum fluctuations in the very early universe. God really does play dice. We have made tremendous progress in cosmology in the last 100 years. The general theory of relativity and the discovery of the expansion of the universe shattered the old picture of an ever-existing, an everlasting universe. Instead, general relativity predicted that the universe, and time itself, would begin in the Big Bang. It also predicted that time would come to an end in black holes. The discovery of the cosmic microwave background and observations of black holes support these conclusions. This is a profound change in our picture of the universe and of reality itself. Although the general theory of relativity predicted that the universe must have come from a period of high curvature in the past, it could not predict how the universe would emerge from the Big Bang. Thus, general relativity on its own cannot answer the central question in cosmology: why is the universe the way it is? However, if general relativity is combined with quantum theory, it may be possible to predict how the universe would start. It would initially expand at an ever-increasing rate. During this so-called inflationary period, the marriage of the two theories predicted that small fluctuations would develop and lead to the formation of galaxies, stars, and all the other structure in the universe. This is confirmed by observations of small non-uniformities in the cosmic microwave background with exactly the predicted properties. So it seems we are on our way to understanding the origin of the universe, though much more work will be needed. A new window on the very early universe will be opened when we can detect gravitational waves by accurately measuring the distances between spacecraft. Gravitational waves propagate freely to us from earliest times, unimpeded by any intervening material. By contrast, light is scattered many times by free electrons. The scattering goes on until the electrons freeze out, when the universe is 300,000 years old. Despite having had some great successes, not everything is solved. We do not yet have a good theoretical understanding of the observations that the expansion of the universe is accelerating again after a long period of slowing down. Without such an understanding, we cannot be sure of the future of the universe. Will it continue to expand forever? Is inflation a law of nature? Or will the universe eventually collapse again? New observational results and theoretical advances are coming in rapidly. Cosmology is a very exciting and active subject. We are getting close to answering the age-old questions. Why are we here? Where did we come from? Thank you for listening to me.
I'm still awestruck. May I now invite our esteemed Council Chairman, Dr. John Chan, to give a vote of thanks to Professor Stephen Hawking.
Professor Hawking, millions of copies of your book, A Brief History of Time, have been sold worldwide. Since news of your visit leaked months ago, the book has been selling like hotcakes in Hong Kong. No doubt all the bookstore owners would want me to say a big thank you to you for coming to our city. But you are not only good for the book business, you are good for our intellect, perhaps even our souls. There is no substitute for seeing a great thinker in the flesh and having his magnificent ideas explained in person. Thousands signed up on the website for a seat by lottery. Hong Kong has bi-weekly lotteries, but we have never had a lottery for a lecture. All of us in this hall and hundreds of thousands more watching live broadcast on television are the lucky winners. Professor Hawking, the impact of your visit will be felt for a long time to come. You and what you stand for have become our obsession. We never knew that the realm of scientific ideas can be so captivating. I can find no words for our gratitude to you for making the long journey from Cambridge University to Hong Kong UST. But we do have a small token to express our appreciation. It is an on-the-spot sketch of the greatest living scientist by one of Hong Kong's most celebrated sketch artists, Mr. Serco Lo. Normally, Serco is better known for sketching horses at the races, but today he has applied his talents to sketching a great scientific mind, one that gallops across the limitless universe from galaxy to galaxy. Professor Hawking, I have the great honor to present to you, on behalf of Hong Kong UST, and through your charming daughter, Miss Lucy Hawking, a special artist rendering of your presence at this historic and never to be forgotten occasion. Lucy, please.